Stern-Gerlach is one of the landmark experiments in quantum mechanics and always presented to introduce the concept of spin. Something always bothered me about this. Stern and Gerlach did their famous experiment in 1822, but a spin was introduced more than 3 years later. The truth is that this experiment had nothing to do with spin. This is the real story of the Stern-Gerlach experiment. Before I get any further, I just want to clarify that the modern interpretation of the results obtained by Stern and Gerlach is indeed the spin of the electron. I am not claiming the opposite, but nobody knew about this concept in 1922. So I always wondered, what exactly were Stern and Gerlach even trying to measure? Otto Stern got his doctorate in physical chemistry in 1912 and moved to Prague to work as an assistant to Albert Einstein. In July of the same year, Einstein received an offer from his alma mater, the ETH in Zurich, and he asked Stern to join him. In Zurich, Stern became friends with Max von Laue, the former assistant to Max Planck, who 7 years earlier, in 1905, had traveled to Bern to meet the unknown author of the theory of special relativity. Von Laue was now a respected professor, after proposing an experimental method that finally ended the debate about the nature of X-rays in 1912. The publication of Bohr's model in 1813 made Stern and von Laue close friends, as they share a dislike for what they called this nonsense of Bohr. They wished for an experiment that could falsify the nonsense of quantum jumps and quantized orbits. Stern was not a theoretical physicist, so he attended all of Einstein's lectures, and he would later recall that one of the most important skills learned from Einstein was coming up with realistic thought experiments to test ideas. In 1914, Einstein was named director of the Kaiser Wilhelm Institute in Berlin and left Zurich. At the same time, von Laue accepted a position at the University of Frankfurt and invited Stern to come as his assistant. Just a few weeks after they moved from Zurich, von Laue was awarded the Nobel Prize in Physics for his discovery of the diffraction of X-rays by crystals, work that he did only 2 years earlier during a stay with Sommerfeld in Munich. With the start of the First World War, Stern volunteered to serve in the German army. After training as a meteorologist in Berlin, he was sent to Belgium, supporting the setup of a physics lab for the military. Given the lack of materials and equipment, the idea of confiscating the physics equipment of the Solvay Institute in Brussels was proposed. Stern knew very well the value of the Solvay Institute for the physics community and secretly alerted Walter Nernst in Berlin about the plans. Nernst was the mastermind behind the creation of the Solvay Institute in 1911, and after Stern's secret warning, successfully used his influence to keep the Solvay Institute untouched during the war. After surviving the crash of the weather airplane carrying him during a mission, Stern moved to Berlin and joined Nernst's lab, where he got trained as an experimental physicist by one of the most recognized physicists of the time, James Franck. Ironically, Stern still could not accept Bohr's model, and now he was being mentored by one of the first to provide experimental support for Bohr's model with his famous experiment with Gustav Hertz right before the war. After the war was over, Stern returned to Frankfurt in 1919, but Max von Laue was no longer there. He exchanged roles with Max Born from Berlin. Born became the head of the physics department and was really impressed by Stern's plans for the small Frankfurt lab. Stern had become great at designing clever experiments, but not yet the best at building them. Fortunately, the physics department had a great technician named Adolf Schmidt. Stern wanted to build a molecular beam to study the magnetic properties of single atoms and molecules in gases. Bohr gave Stern full support and provided the necessary and scarce funding. After a year of work, the molecular beam was finally working. Stern used it to experimentally confirm for the first time the Maxwell distribution of velocities in a gas. After this success, Stern noted that no experiment had been designed to challenge what he and von Laue called Bohr's nonsense. Bohr's model could explain the spectral lines of hydrogenic atoms and the Frank-Hertz experiment, but the wartime prevented the design of an experiment specifically planned to test the model. The 4 years of war not only prevented the kind of experiment that Stern wanted, but also during this time, Bohr's model had been refined and extended by Sommerfeld, as I showed you in the last video. Crucially for Stern, a few months after the publication of the Bohr-Sommerfeld model in 1916, Sommerfeld himself and his former student Peter Debye had independently discovered a unique property of the new atomic model that could be tested in the lab. In the last video, I showed you how Sommerfeld proposed a general method for constructing the quantum version of a classical theory using what we now call the Wilson-Sommerfeld quantization rule. Using this rule, Sommerfeld introduced elliptical orbits and solved the mystery of the fine structure spectral lines. In that video, I showed you that Sommerfeld imposed a quantization over the azimuthal angle, just like Bohr, and the radial coordinate to describe elliptical orbits. But you might have noticed that no quantization over the polar coordinate was imposed. After all, electrons should be able to move in 3 spatial dimensions. Sommerfeld, just like Bohr, assumed that electron orbits lie on a plane like the orbits of the planets around the Sun. This assumption makes sense for planets that form from a common disk of material, but electron orbits are not required to satisfy this assumption. Sommerfeld quickly fixed this. In October 1916, he published a new article allowing electron orbits in 3 dimensions instead of being confined to a plane, for which he had to introduce a third quantum number. Using energetic and geometric conditions, he found that these quantum numbers could not take any integer values. They must satisfy some conditions. Sommerfeld initially called these quantum numbers n1, n2, and n', which later became simply n, k, and m. They satisfy the following relations. N is a positive integer. K is a positive integer less than or equal to n. And m is an integer in the range minus k to plus k. These numbers are respectively called the principal, azimuthal, and magnetic quantum numbers. In modern notation, k was replaced by L equals k minus 1. Sommerfeld considered the atom in the presence of an external magnetic field, which defines a preferred direction in the space of the experiment. Without loss of generality, we can choose our coordinate system so that the z-axis points along the magnetic field. Although the angular momentum of the electron points in some direction in space, Sommerfeld argued that any measurement of the angular momentum corresponds to a projection of the angular momentum along the axis defined by the magnetic field. Therefore, according to Sommerfeld, the angular momentum quantization implies Lz equals mh bar. If we call alpha the angle between the angular momentum vector and the z-axis, we can write the projection of the angular momentum as Lz equals the magnitude of the angular momentum times cosine of alpha. Then the cosine of the angle becomes this expression. From simple geometry, the magnitude of the angular momentum vector can be written as the maximum value that Lz can take, from where we get the ratio between magnetic and azimuthal quantum numbers. Here we discovered that the angle alpha is restricted by the values that the magnetic and azimuthal quantum numbers can take. The directionality is now quantized, meaning that the electron can orbit the nucleus only in very specifically oriented orbital planes. This feature became known as space quantization, and later simply renamed angular momentum quantization. Let's see an example. The ground state, or lowest possible energy, is defined as the level with the lowest principal number, n equals 1. This level contains 3 states. Since n equals 1, the azimuthal number can only take the value k equals 1, from where the magnetic quantum number can take the values 1, 0, and minus 1. Using the formula that we found for the angle between the z-axis and the angular momentum, we find that the first state represents an electron with angular momentum parallel to the z-axis. Similarly, the other two states correspond to orbits with the angular momentum vector pointing perpendicular and anti-parallel to the axis defined by the external magnetic field. For the next energy level, we have 8 different states. The first 3 are similar to the previous level, whereas the other 5 configurations have an angular momentum vector twice as long with 2 tilted orbits, in addition to the states parallel, perpendicular, and anti-parallel to the magnetic field. Coincidentally, Peter Debye, one of the brilliant former students of Sommerfeld, also discovered this using advanced mathematical methods. Their articles were published together in October of 1916. In the following months, Bohr suggested that the quantum state with m equals 0 would be unstable, so for the ground state, only the other 2 states would be observable. In 1920, Wolfgang Pauli, another of Sommerfeld's great students, introduced the concept of magneton. This is the magnetic moment produced by an electron orbiting the nucleus. To study the forces acting on the atom in an external magnetic field, a very important concept is the so-called magnetic moment, denoted by the Greek letter mu and given by the current times the area around which the current circulates, pointing perpendicular to the area. The electric current generated by an orbiting electron can be calculated as the ratio of its electric charge and the period of the orbit t. Using high school circular motion, we obtain this relation. Plugging this back into the definition of magnetic moment, I will multiply and divide by the electron's mass, from where we find that the magnetic moment is a constant factor times the angular momentum L. Useful for our discussion here is the z component of the magnetic moment, which becomes a constant times the magnetic quantum number m. Pauli called the overall constant Bohr's magneton. After learning about Sommerfeld-Debye space quantization in 1921, Stern knew exactly what to do next with his molecular beam, prove that space quantization was wrong. Following what he learned from Einstein, Stern came up with his own thought experiment. He envisioned sending a beam of magnetic atoms through a magnetic field in a vacuum chamber and measuring the deflection of their paths using a detector on the other side. Since the atom is neutral, no Lorentz force would affect its motion. The only force acting on the atom would be due to the magnetic moment, which is what Stern wanted to measure. From electromagnetic theory, the potential energy associated to a magnetic moment, mu, in the presence of a magnetic field B is minus the dot product of these two vectors. Choosing the z-axis to point along the magnetic field, the potential becomes minus mu z times p, where mu z is the component of the magnetic moment along the z-axis. The force is given by minus the gradient of the potential, which in Cartesian coordinates becomes this, making the field uniform along the x and y directions, but non-uniform along the z direction, reduces this expression to mu z times the gradient along the z direction. This shows that if the magnetic field is uniform, then there will be no force. Therefore, a non-uniform magnetic field is necessary. Stern proposed to use a magnet with a pointy south pole, so that the magnetic field lines are not uniform. This inhomogeneous magnetic field has a non-zero gradient, and this produces a force that will deflect the atoms in the beam which Stern set up to measure. According to Sommerfeld and Debye, the original beam should split into 3, corresponding to the 3 predicted states. 1 part deflected up, 1 deflected down, and 1 non-deflected part. Bohr insisted that the undeflected component would not appear because of the instability of the state with m equals 0. Stern wrote his idea and published it in August of 1921. In this article, he described all the details of his thought experiment, the force that each atom in the beam will experience, and more importantly, the 2 possible outcomes of the measurement. If atoms behave according to classical physics, their magnetic moments will be randomly oriented in all possible directions in space, contrary to the Bohr-Sommerfeld-Debye prediction. As a consequence, when passing through the non-uniform magnetic field, some atoms would be deflected up, others deflected down, and everything in between for atoms with magnetic moments oriented in random directions. The final result would be a spread of the original beam of atoms up and down along the direction of the magnetic gradient. On the contrary, if the predictions of the Bohr-Sommerfeld-Debye atom are correct, since the magnetic moment is proportional to the angular momentum, this could only take discrete directions in space. For this reason, atoms would be deflected up or down, but nothing in between, splitting the atomic beam into two, according to Bohr. Stern stressed the importance of this experiment in his paper. The experiment, if successful, results in a clear decision between the quantum theoretical and the classical view. This is the crucial statement of the experiment designed by Stern. Its result will unquestionably confirm or disprove quantum physics. Ironically, Stern's proposal was not celebrated. Some theorists believed that space quantization was nothing more than a useful mathematical description. In fact, this time, Max Born was reluctant to provide any of the scarce funding. In his autobiography, Born wrote, "It took me a time before I took this idea seriously. I always thought that space quantization was a kind of symbolic expression for something which you don't understand." But Stern took the idea literally. I tried to persuade him that there was no sense in it. But Stern insisted that this measurement was worth a try. During this time, a new professor arrived at the Institute for Experimental Physics in the building next door, Walter Gerlach. Gerlach was a respected experimental physicist trained by the great Wilhelm Paschen, who in 1916 confirmed the fine structure lines in helium predicted by Sommerfeld. Gerlach arrived with plans of studying magnetic properties of atoms by deflecting a beam using a magnetic field. He had never heard of space quantization. After they met, Stern told him, "With a magnetic deflection, you can also do something else. Do you know about space quantization?" After explaining the idea, Stern asked him, "Shall we do it?" Gerlach was immediately on board. Stern had designed a beautiful experiment. Gerlach had the experience to make it a reality. Stern finally convinced Born, who gave him all his support, and instructor Mr. Schmidt, the lab mechanic, to assemble the necessary pieces for the apparatus. Soon after Stern and Gerlach teamed up and began building the experiment, the post-war reality put the whole project at risk. The German economy was in ruins, which prevented access to key components. Stern and Gerlach desperately needed money for equipment. This was also a period in which Einstein became a celebrity after the confirmation of the deflection of light predicted by general relativity. Max Born took advantage of this public interest and gave a series of lectures about relativity for the general public, for which he charged an entrance fee. All the money went to buy components for the Stern-Gerlach experiment. The country was also experiencing a period of hyperinflation that made money lose its value quickly. Soon the Stern-Gerlach experiment was at risk once again. In Berlin, Einstein was also an advocate of this experiment. Now as director of the most prestigious scientific institute in Germany, he got access to some funding, which he channeled to Max Born to support the experiment. After almost half a year of work, Stern and Gerlach had their experiment built and running. An oven produced a low-intensity beam of silver atoms that was collimated by two consecutive and very narrow rectangular slits. Then the beam encountered the non-uniform magnetic field to deflect the atoms, followed by a detection plate. The low intensity of the beam allowed the atoms to go through the apparatus one at a time. This was done to avoid any interaction between atoms in the beam that could generate a false signal. The downside was that a low-intensity beam produces a weak signal to be detected. Therefore, the experiment needed to run smoothly for several hours while a glass plate slowly collected the silver atoms. The rectangular slits made the beam to have the shape of a very thin horizontal line, less than a millimeter in length. They had to take a microscopic photograph to properly analyze the result. When the German currency collapsed, the Stern-Gerlach experiment was at risk again. Stern notified Born that they could barely keep the lab running. In one of those coincidences of history, Bohr was meeting a friend who was traveling to New York, and as a joke, he told his friend, "If you find a German American who is still interested in the old country, tell him I need dollars for an important experiment." A few weeks later, Bohr received a postcard from New York. His friend told him about a banker who had family in Frankfurt and wanted to make a donation to support the experiment. The postcard read, "Write to Henry Goldman." Henry Goldman was one of the founders of Goldman Sachs, a financial services company that exists today as one of the largest investment banks. Born described it as follows: "At first, I took it for another joke, but a nice letter was composed and dispatched. Soon, a most charming reply arrived with a check for some hundreds of dollars. After Goldman saved our experiments, the work on the Stern-Gerlach experiment went on successfully." Stern and Gerlach also received donations from local companies like Messer and Company that gave them a full supply of liquid air for the cryogenic components of the experiment. Messer exists today as a large provider of gases for medical and industrial applications. By the way, this video is not sponsored by Messer or Goldman Sachs, but any donation from them is welcome. After months of work, when Stern and Gerlach finally managed to run the experiment without a pump or any other component failing, they had to shut everything off, open the vacuum chamber, and remove the plate. They found no signals of the expected silver film on the plate. Stern described it like this: "After venting to release the vacuum, Gerlach removed the detector plate, but he could see no trace of the silver atom beam and handed the plate to me. With Gerlach looking over my shoulder as I peered closely at the plate, we were surprised to see gradually emerge the trace of the beam. The expected signal literally faded in on the plate in front of their eyes when Stern took it in his hands. They soon realized the reason for their lucky strike. They smoked in the lab. My salary was too low to afford good cigars, so I smoked bad cigars. These had a lot of sulfur in them, so my breath on the plate turned the silver into silver sulfide, which is jet black, so easily visible. It was like developing a photographic film. They had to repeat this process with and without the magnet. Unfortunately, they did not observe the widening of the beam nor its splitting. In late 1921, they reported the details of the experiment and their inconclusive results. Just like Born at the beginning, Peter Debye was surprised to learn that Stern and Gerlach had taken the concept of space quantization so literally. Gerlach remembered Debye commenting, "Surely you don't believe that the spatial orientation of atoms is something physically real. That is only a prescription for the calculation, a timetable for the electrons." This was very demoralizing, but they kept trying. In 1921, the University of Göttingen was looking for a new leading theorist to replace Peter Debye, who moved to Zurich. Max Born left Frankfurt to create one of the leading centers of theoretical physics, where a few years later quantum mechanics would be formulated. Stern also left Frankfurt after accepting a position at the University of Rostock in northern Germany. Gerlach continued the experiment alone and continuously reported to Stern, who would visit him regularly. On February 7, 1922, Gerlach spent the night with the apparatus running smoothly, while the glass slate collected the silver atoms one by one. The next morning, Gerlach opened the vacuum chamber and removed the detector. After examining the microscopic photograph, he became the first person in the world to know the answer to the question proposed by Stern almost a year earlier. This is the microscopic photograph that Gerlach obtained in the absence of the magnetic field, the expected horizontal line showing that the beam was perfectly aligned. The second image, obtained with the magnetic field, shows how the original beam split into two. just like Bohr had predicted, according to the Bohr-Sommerfeld-Debye model of the atom. The two lines merge at the edges of the beam because the magnetic gradient is stronger at the center and weaker at the two edges. Gerlach immediately sent a telegram to Stern in Rostock, sharing the news. Stern had been convinced that the experiment that he designed would finally put an end to the nonsense of Bohr, but it ended up doing the exact opposite. This reminds me of Robert Millikan, when he attempted to prove Einstein wrong with an experiment that confirmed all of Einstein's predictions for the photoelectric effect. In an act of scientific integrity, Otto Stern accepted the experimental evidence, updated his preconceptions, and changed his mind. Stern and Gerlach showed the world with certainty that there was no room for classical mechanics in atomic physics.